Hello and welcome back to Counting Rocks: An Introduction to Combinatorics at CSU. Today we're going to be talking about graph coloring, in particular coloring the vertices. A proper coloring of the vertices of a graph is a coloring of each vertex with some color such that adjacent vertices always have to use different colors. Here's an example of a coloring that's not proper. I put Y's for yellow and G for green and W for white and R for red here so we can easily see the colors. And I colored two adjacent vertices yellow. These two vertices are connected by an edge, that means they're adjacent, and they're both yellow, so that's not a proper coloring. But here's a proper coloring. We use yellow, green, red, and white in some way, where we can repeat colors, Y and Y, but they're not connected by an edge, so that's okay. So if they're directly connected by an edge, they can't be the same color. But here, every edge is okay. Y and W, W and Y and R and G and Y and R. So all of those edges have different colors on each end, and so this is a proper coloring. Now, one of the most famous places proper colorings come up is in coloring maps. This is a famous application of coloring. If you would just have a map, and ignore the graph for a minute, look at the map underneath. Imagine this is a map of states in some country or countries in some continent, and some of them share borders, and you want to draw a map of them and use a small amount of colors for the map so that two states that share a border do not have the same color. For instance, if we colored this big state pink and also this one pink, it would be hard to tell that they're different states. You want them to have different colors if they're adjacent. Well, we can model this as a graph coloring problem by drawing one vertex for each state and then connecting those vertices if those two states share a border. So for instance, this blue state is connected to this brown state, but it's not connected to this yellow state because it only shares a point with that yellow state, not an actual physical border. So we can always draw a planar graph that models coloring maps like this, and we want to know what's the smallest number of colors we need to be able to guarantee that we can color the map in a way that no two adjacent states have the same color. Now, answering this isn't the same as actually generating that coloring, but just theoretically, how small of a number of colors do we need? Because we also don't want to just use a different color for every state. That would make the map look too busy. So we want to make it simple, but also distinguish every state from each other. We're also making some assumptions in this problem, in particular that every state is a connected, bounded region. So we don't have, for instance, a state that's like a substate of some other state that's just sort of contained inside the other state, and the state has like a hole in it. So we just imagine sort of connected, bounded regions that are all filled in as one state, and then the things bordering it are different states. So the four-color theorem says that every planar graph has a proper coloring with only 4 colors. We used 5 colors on the previous example, but we can also use 2 G's here to make the graph a little bit more simple. For instance, we already had 2 pinks, but we can also color this state and that state the same color because they don't share a border. Here's an example of a way to color this map in 4 colors. Some graphs only need 3 colors, but you can make a map complicated enough that you do actually need 4 colors as well. Now, this motivates the notion of chromatic number of a graph. The chromatic number is the smallest number of colors needed to make a proper coloring of the graph. So for an arbitrary planar graph, if it's complicated enough, the chromatic number is going to be 4 by the 4-color theorem. But you can make a graph with chromatic number 5 if it's not planar. For instance, K5, which we know is not planar by Kuratowski's theorem, and its chromatic number is 5 because every vertex, all 5 vertices, are connected to all the other vertices by an edge, and so all 5 vertices have to be different colors. So you need 5 different colors. So complete graphs are hard to color. You need at least n colors for a complete graph Kn. Whereas a bipartite graph is much simpler. Its chromatic number is always only 2 because we have a left set and a right set and some edges going between them. And so it suffices to just color all the things on the left set one color and all the other things on the right set a different color. Then there will be no adjacent vertices sharing the same color. Now, how many colorings are there once we know it can be colored? How many colorings, for instance, of P3 have 2 colors? Let's say we're just using green and yellow. Well, if we have a path graph P3, we have to alternate along the path for it to be proper. So we could either do GYG or YGY. So there's 2 colorings of P3 with 2 colors. But this gets a little more complicated if you allow 3 colors or 4 colors or 5 colors. So in general, how many with n colors? Well, we can treat this as just an ordinary counting problem using the multiplication principle. There's n ways of choosing how to color the first vertex, and once we've chosen that one, there's n-1 ways of choosing choosing how to color the next vertex because it can't agree with that previous vertex, so we only have n-1 left. Also, this one has n-1 colors that don't overlap with the color we just chose for the middle vertex. Now, we don't have to worry about the connection between the first and third because there is no connection. They're allowed to be the same color, they don't have to be the same color, there's no restriction. So it's going to be n times n-1 times n-1. Notice that this is a polynomial in n of degree 3. In general, the chromatic polynomial is going to be a polynomial that describes how many ways we can color with n colors for that particular graph. And we write it chi sub p3 of n in this case. So chi sub p3 of n is n times n-1 times n-1. We can expand this out as a polynomial as well if we want, n cubed minus 2n squared plus n. Now it turns out that this kind of count is always a polynomial called the chromatic polynomial. The function chi g of n, counting the number of proper colorings of graph G with n different colors, is the chromatic polynomial of the graph. Let's do another example. How about C3? Is that a different polynomial? Well, yes, because now if we choose how many ways to color the first vertex, if we have n colors, there's n ways to do that. And then if we want to color another vertex, say this one, now there's n-1 ways of choosing a color that's compatible with that one. And then this one can't be either of the two colors that we chose before. And so there's only n-2 ways of choosing that color. So now it's n times n-1 times n-2, which is a different polynomial than we got for the path graph. The way we calculate chromatic polynomials in general is not by this case-by-case analysis and multiplication principle, but rather by recursion, and this recursion also tells us that it's always a polynomial because we're going to add two polynomials to get another polynomial. But what we do is we use deletion and contraction, which were two operations on graphs that we introduced in the context of graph minors for planar graphs. So to remind ourselves, G minus E is the graph formed by deleting an edge E from G. For instance, if this is a graph G, and here's our edge E on the top, then we delete this edge to get G minus E, and it's just this U-shaped graph where we actually just erase that edge between those two vertices, but we leave the vertices. And the contraction of G by E is formed by actually shrinking this edge down to a point, and so we would get a triangle graph in this case. So here's G with E contracted, and here's G minus E. And so the formula is that the chromatic polynomial for G is the chromatic polynomial for the deletion of E minus the chromatic polynomial for the contraction. Now why is this? Let's analyze this by thinking about the colorings. If we're coloring these four vertices, what we want to make sure is that, for instance, this vertex cannot be the same color as that one. Let's focus on that particular edge. And let's assume all the other edges have good colorings as well. So if we have that property, well, with the difference between that one and here, if we have a proper coloring here, we still need this edge, which comes from that edge, to be proper, so you have different colors on each of these edges. But now this vertex is just one color. That represents coloring both of these vertices the same color, which is not what we want. Whereas in this graph, we have too much freedom. Since we deleted that edge, now we're allowed to color these two vertices the same color as each other, or we don't have to. They could be different as well. So if we take the chromatic polynomial for this graph, and we subtract the colorings for this graph, which record when these two are colored the same color, then we get all the colorings of this graph in which these two are forced to be different colors, which is the same as the proper colorings of this graph formed by adding that edge back in. So that explains this formula. So now you try. What is the minimum number of edges needed in a graph with 5 vertices in order for the chromatic number to be 5? We saw that K5 has a chromatic number of 5, but can you delete some edges from K5 and still have it need 5 colors, or do some of them only have chromatic number of 4 or less? What's the threshold there? So that's all for today, and I'll see you next time.